ionospheric heaters. The most famous one is named Haarp, based in Alaska, credited with the military application of changing the world's weather, heating our upper atmosphere to deorbit rogue satellites. It's claimed it blocks international radio signals, and it's even credited to be able to send bolts of electricity out of the sky and mind control. But is any of that really true? Today, I'm highly privileged to share with you an interview with a real ionospheric heating scientist who knows exactly how it works and what it really can do. Meet scientist Antti Kero. Antti works in Finland's most important geophysical science university, looking at our ionosphere, and he has access and uses daily ionospheric heaters left over from the Cold War. So let's explore the myths of ionospheric heating, the history, and the hidden truth. So, Antti, it's so great to see you, and thanks for joining us. Professor Palmroth covered the ionosphere so brilliantly for my YouTube viewers and the people who like my channel who are interested in science. But of course, they all asked me about ionospheric heating and all the conspiracy theories about ionospheric heating. And I thought today it would be great to speak to you, somebody involved in that science and that field, and to dispel some myths and to go over what actually is going on with human intervention with the ionosphere. So my first question is, doing some research and what I basically know from my science research is it true that it became possible that the ionosphere could be modified due to Radio Luxembourg modifying modifying other people's radio transmissions when they bounce, as we know, off the ionosphere? Tell us about the Luxembourg Effect, and when was that?
Yeah, thank you very much for the invitation, first of all, and it's very nice to talk about heating as a scientific perspective. And you are absolutely right. This so-called Luxembourg effect was the first heating experiment, although it was unintentional one. It was in 1930s, 1933, and at that time, well, obviously radio was invented, and also it was invented in this famous Marconi's experiment that radio waves can be propagated, or ionosphere can be used as a mirror for radio waves.
Right.
And in this, what happened in this Radio Luxembourg case was that there was another amplitude modulated radio station. I think it was the transmitter was in Peromünster, and the receiver was in Eindhoven.
Right.
And this very powerful Luxembourg station was in the middle.
Yeah.
And it turned out that you could hear in the background of this other radio station from Peromünster also this Radio Luxembourg. And that was a puzzle, because that was totally in a different frequency. And it was explained in a scientific journal Nature later that in fact the possible mechanism which caused this cross modulation was actually heating of the radio path between the transmitter and the receiver.
Right.
So this Luxembourg station, as amplitude modulated, station that was capable of modulating
Right.
the ionosphere, which act as a mirror in between the transmitter and the receiver. So that was really the early invention of man-made experiment in space in this sense.
It's just a brilliant story. I remember back in the 60s, somebody told me that Radio Luxembourg was so powerful that somebody managed to take an induction coil in their chicken house and use it to heat the chicken house, which I think is just fantastic. Anyway, that's just brilliant. But so I take it that the Luxembourg effect was observed, and some smart person, and I would have thought that, maybe it's possible that we could attenuate or modify somebody else's radio broadcast by affecting the bounce layer, one of the ionospheric bounce layers. And so I'm going to use the word carefully. It was the first idea that this outside part of our atmosphere could be weaponized. So was the first applications for human intervention into the ionosphere a military project before science came along?
Well, I don't think that the military application was so much to do with disturbing the radio transmissions. The reason why I'm skeptic about this is that this frequency modulation, which was invented later, that actually solved the whole problem. I mean, frequency modulation is much more robust against the amplitude changes, and that basically solves the problem. You are right in the sense that in the very beginning of these heating experiments, military applications or military organizations were very interested in this. But the reason was more to do with using the ionosphere as a huge radio antenna. Because by modulating the currents, or basically conductivities in ionosphere, makes it possible to use or to use ionosphere as a very long wavelength transmitter for radio waves, VLF waves.
Right.
And that in turn is very useful for communicating to submarines.
So the ionosphere, the idea was the whole of the Earth, or a large section of the ionosphere, could be vibrated by radio frequency for VLF waves. And so a submarine at a long distance could pick up a message. Is that?
Yes, something like that. Of course, it is relative what is the large part of the ionosphere, but basically the ionosphere above the heating facility can be modulated. So it is typically something like 10 degrees wide beam, and obviously in the global scale that is a very tiny spot in the sky which is modulated, but nevertheless that can be used as a larger antenna. And but the problem in that system is that worked very nicely in some days, but then when the ionospheric conditions are, let's say, disturbed in the wrong way or too quiet or something, then this mechanism is not that suitable for sending these waves. Or and these transmitters for the submarines, which are basically nuclear submarines under the water, it's strange to think, but they don't know if the nuclear war has started over there. So there must be some kind of beacons explaining them that we are still here.
Right.
Don't push the button.
Right.
So we cannot use anything unreliable for this kind of messages.
Right.
And I think this military interest on this heating experiment was more like a prototype rather than the actual method of communicating those soldiers in the submarines that we are still here. And that's why there are special transmitters designed for this purpose only, and they are not heating facilities.
They're combined VLF or ultra ULF stations that also could use the ionosphere to communicate with submarines. They're often associated to send out this "don't fire your missiles, hold" message, which is the constant message, which all you need to do is to tune in to check that it's still saying the world is safe, the world is safe, don't fire.
Well, obviously, I mean, it's classified what they send. Those are also modulated transmissions, basically coding some kind of message. And of course, we don't know what is that for sure, but perhaps they are some kind of beacons for navigation, and perhaps the message is very simple.
Right.
That everything is fine, and so that is my, obviously I'm not a military scientist, so I don't know much about it, but this is my educated guess what is going on.
Next question. So so that turns the whole thing on its head. I always assumed that the military were interested in turning off radio transmissions, and you've just totally said the opposite, which is so interesting, that they were using ionosphere as a giant transmitter. Why do you think the early most of the man-made ionospheric heaters are in extreme polar latitudes?
Well, that is to do with the academic interest in heating science, and that is basically where the auroral oval and radiation belts take place.
Right.
If you think about the magnetic field of the Earth that hits us in the magnetic poles, of course, and that is where you have energetic particle precipitation from the Earth's magnetic field or Earth's magnetosphere. And so most of this interaction between the space weather and atmospheric interaction that happens in the polar latitudes, and heating science is aimed to study these effects kind of in an active way. One other thing is that these heating experiments are they benefit from the vicinity of other instruments which are supporting these measurements and basically are used for measuring these heating effects. So the one which I have been using, which is this IceCat heating facility, that is obviously next to the IceCat radar. And it is there because IceCat radar is there, and IceCat radar is there because it's an interesting place. So like in terms of magnetosphere. So I think that is the reason. But one of the first heating facilities one of the heating facilities made in the 80s was in Arecibo, so it wasn't so high in latitude.
Yeah, no, the Arecibo story is just absolutely fascinating because it kind of breaks away from the polar positions of Alaska and Norway, Finland, and maybe Antarctica. But it's let's bust some myths about Arecibo because everybody thinks Arecibo is this SETI radar radio telescope that we've all seen in the film Contact. And sadly, it fell down. Probably due to lack of maintenance and lack of funding. But if you really look at the history of Arecibo, and you've already mentioned it in the context of an ionospheric heating station, isn't it true that there's an ionospheric heater, or there was an ionospheric heating radio antenna, and that the Arecibo dish was actually is a radar dish looking for the effects of this heating? Was that its main role when it was first built?
Yes, it was a radar in the first place,
Right.
but no for the heating experiments. That was later addition. But well, the story of Arecibo radar or facility started because it was there was a theory that you can have incoherent scattering from plasma from ionosphere, but they calculated that that will be so tiny backscattering that you need to have this kind of huge antenna in order to see that backscattering.
Right.
So the collective area or collection area for this tiny bit of backscattering from, let's say, megawatt range transmitter, so tiny bit comes down from these free electrons from ionosphere. That was basically calculated, and then it turned out that this backscattering is still very tiny, but it is much stronger than expected.
Right.
So in fact, that was a bit of an overkill to make this kind of huge antenna.
Yeah. Right.
And that was it's a bit technical, but the early scientists or early theoreticians, they didn't understand that scattering is actually enhanced by the fact that electrons are not that free in plasma, but they have to move along the ion acoustic waves, and that is very beneficial for this business. So I think this antenna was roughly by factor of 10 too big to. Right. I mean, they just wanted to see something, and the backscattering was much stronger. But on the other hand, that turned out to be very beneficial for many science applications, not only the radar, incoherent scatter radar business, but also the radio astronomy and SETI. Right. So Arecibo radar was the largest and most beautiful radar in the world, and it's very sad that in 2020 it was destroyed by
the hurricane. Yeah.
Hurricane, and that was the end of it, really.
Yeah, it's unlikely that it will be rebuilt.
Yeah, I hope that U.S. funding agencies come to their senses and rebuild that.
Oh, it would be great. But it's good to bust some myths, because I don't think people really understood why it was built and what it really did and what its capabilities, its major capabilities were. Although, as you said, it did have other functions as they put in different antenna later in its life. Oh, so that's fantastic. So atmospheric heating is not going to send a beam of death into your house, and it's not going to change the world's weather. And it's also probably going to be very hard to make an ionospheric heater that would deorbit a satellite. And that's a lot of people are interested in that. Was there research in, the kind of oversimple idea is if the part of the ionosphere could expand into the path of a low Earth orbit satellite, you could maybe slow it down to a point every time it went round, you could target how it was deorbited. Is that a complete myth? Obviously, it does work because, as we talked in the last film, when the ionosphere naturally expands due to space weather, it can affect low Earth orbit satellites. But have you ever come across any projects that could literally deorbit a satellite from Earth?
Well, to me, it sounds a bit science fictional. First of all, I think many of these misunderstanding concepts related to heating experiments are because the heaters don't really heat the atmosphere.
Right.
They heat the electron gas or plasma in the ionosphere, and ionosphere is partly ionized part of upper atmosphere. So we call that ionosphere, where solar precipitation or solar X-rays are,
right,
or EUV is detaching electrons from neutral atoms that makes a pair of positive ion and electron, and that is called ionization. Okay, perhaps these things you have already covered.
No. It's good to repeat what plasma is and what ionization is, and you've just done it very clearly. Thank you. Yeah.
So I just want to point out that this electron heating is really electron heating. So even the ions are not heated in the in these experiments, because ions are very heavy compared to electrons.
Right.
Electrons are very sensitive on very tiny radio wave intensities.
Right.
So if you calculate the intensity of the most powerful heaters in let's say 100 kilometers,
right,
then the intensity is some milliwatts per square meter. So it is clear that it is not any Death Star capable of pretty much anything. It is a very tiny energy, which is still important for the electrons, because they are they are small and they are easy to move back and forth, and as a consequence, this electron temperature can be increased by these heating experiments by a factor of 10 quite easily.
Right.
So, and many phenomena in the ionosphere, let's say conductivities or chemistry, or also plasma phenomena, they are electron temperature dependent. So we can use the ionosphere as a space laboratory or space plasma laboratory and do active experiments.
Right.
So there is lots of potential of making these kind of effects, which are dependent on the electron temperature genuinely, but there are also very serious limitations in trying to let's say change the trajectories of satellites.
Right.
So one could imagine that we enhance, let's say, ion outflow, because of there is some evidence that can be done, and perhaps that could have some kind of impact on satellites. But I would say that no, it doesn't work, because it is simply these energies needed. It is hard for me to see that
Right.
not to mention that we are changing, let's say, weather,
Right.
because the energies needed to change the weather are completely in different order of magnitude. So these heating facilities, they use typically megawatt of power or 2 megawatts of power. That sounds big, and the electric bill is quite big, but still, if you think about 1 megawatt of power in Finland, we use electric saunas.
Right.
So a small village turn the electric saunas on every Saturday at the same time, and that equals to this heating
It's the
power.
same, right?
So yes, and someone calculated that if there is an asphalt below the antennas which are
Right.
used for these heating facilities, the solar power absorbed by this asphalt is greater than the electric power.
That's
So,
great.
so that may puts that into perspective. That
It does.
that
It does. Yeah. So we're coming to the end of our time that we have. So let's quickly talk about what your current research is and exciting new developments in Finland.
Yes, we have recently launched, or recent years launched, our first satellites. These kind of microcube satellites, which are very popular at the moment, these few kilograms payload satellites, and the recent paper I was involved with my colleague Esa Kallio, using the so-called Suomi 100 satellite, which translates to Finland 100.
Okay.
That was Finland 100 years celebration satellite.
Okay.
And that had the radio receiver on board, so we could listen to the actual trans-ionospheric propagation of the heating signal. And we could, for the first time, measure this kind of nonlinear effect, that when we send this radio wave up to the skies, it really heats the ionosphere, right, and that changes the propagation of that very same radio transmission. So we were kind of doing the Luxembourg effect to our own signal, right, and that has been known that should take place, I mean, since really the Luxembourg effect, but this was the first time it was measured from the space. I mean, through the ionosphere.
No, that's fascinating. Yeah.
Yeah. So that was quite nice kind of demonstration of well, the power of these small satellites. They are capable of doing real science in some reasonable money.
Right.
And also this. That was basically basic research related to this.
That's fantastic.
Old radio science, but also it really emphasized how tiny is this effect, or right, how modest is actually this intensity of the radio wave, because it was, for the dedicated radio receiver, it was you could hear this signal only something like a few seconds, right? Because that is when the satellite was in the beam of the heater, and yes, so to change the trajectory of that satellite, yeah, and to actually hear the signal, it's it is totally different ballpark of a problem, and
right.
Yes. So that is what I have been recently doing with heating experiments. Obviously, I'm interested more broadly on interaction between the solar activity and space weather and the polar region
Right.
ionosphere. So that is my framework, but and heating experiments, that is just one aspect of it. But
Oh,
nevertheless,
it's great, and I'd love to talk to you longer about this. You've covered so many good topics, but we're coming to the end of this Zoom call session, and I'd just like to thank you so much. I will put links to the CubeSat and your research for my viewers to read you about your work. But and Antti, yeah, it's just brilliant. You've busted so many myths. And you've put our world into context about the size of our ionosphere and how minimal we are as humans in actually affecting this global part of our atmosphere. So thank you very much for today. And it's been an absolute pleasure to talk to you and all your wonderful work in Finland. Thank you.